Look inside a modern jet turbine, and you are looking at pure chaos. Billions of air molecules are compressing, igniting, and accelerating at supersonic speeds. If you tried to calculate the total energy of this flow by tracking every single particle, the math would quickly become impossible. The sheer scale of movement breaks our standard equations. To make sense of it all, we have to cheat. Before we do a single calculation, we draw an imaginary boundary. We slice a specific piece out of the universe and call it our system, leaving everything else as the surroundings. We define these boundaries based on the data we need, applying one of two distinct methodologies to analyze the same physical space. Making the right choice between these two lenses is the crucial first step that turns an overwhelmingly complex reality into a beautifully simple equation. The first approach is what physicists call a control mass, or a closed system. Here, we draw our boundary around a specific fixed quantity of matter. Whatever atoms are inside, stay inside. Nothing is allowed to cross the line. But closed is a bit of a misleading term. It doesn't mean the matter is trapped in a rigid, unmoving cage. Energy can still enter and leave. In this piston cylinder, our dotted boundary surrounds only the gas. If we apply heat, the gas expands and pushes the piston upward. The boundary stretches to contain the exact same molecules as they take up more space. Tracking the total energy here is straightforward. We take the heat added from beneath, subtract the boundary work the gas does by pushing out, and we have our answer. This bag of stuff approach is perfect for sealed, contained environments. It is the exact accounting method engineers use to design combustion cylinders for automotive engines. Yet, if you try to use a control mass for a device where matter is continuously rushing in and out, the math completely falls apart. Think about a massive jet engine in a hangar. Air and fuel are constantly pulled in, mixed, and exhausted. Tracking a specific, sealed bag of atoms through that mess is impossible. So we switch to our second lens, the control volume, or an open system. Instead of following the matter, we watch a fixed region in space. The boundary of this volume, the control surface, doesn't have to be a solid metal pipe. It can be an invisible plane drawn right across thin air, acting like a checkpoint. Imagine a flowing river. The control mass approach drops red dye into the water, following its exact shape as it twists downstream. A control volume is entirely different. You hold an empty picture frame in the water, simply counting the flow passing through. By shifting our focus from a moving actor to a fixed stage, we can easily analyze any machine with an open-door policy. Opening the boundary creates a new headache for the first law. When mass flows in, it drags its own energy. Entering a pressurized space requires force to displace the existing medium. This is flow work. Thermodynamics bundles this into a single property, enthalpy. By balancing the enthalpy entering and leaving, engineers calculate the exact power output of massive industrial steam turbines without tracking individual atoms. Enthalpy becomes the primary energy currency for open systems, letting us balance the books on complex machinery at a macro scale. This framework is so robust that we can use it to analyze violently unsteady events. By drawing a moving control volume along with the exhaust of a supersonic rocket engine, the chaotic explosion becomes a predictable flow. Scientists scale this exact same accounting method up to the size of a planet. We draw macroscopic control volumes around cities, rainforests, and the global atmosphere to track massive flows of carbon and water through Earth's ecosystem. But if you look closely at the universe, you won't find any control masses or volumes. There are no actual dotted lines floating in space. These boundaries are entirely human inventions. They are mathematical lenses we overlay onto the physical world to untangle the chaos and expose the elegant conservation laws running the cosmos.